Okay, everyone. Afternoon. Once again. Right. So last time we began the quadratic residues chapter 8, with a fairly leisurely introduction via considering the idea of solving a quadratic congruence. We began looking back at an old favorite, the quadratic equation. Ax squared plus bx plus c equals 0. What are that solutions? Everybody knows the well-known formula, quadratic formula, involving the square root. What we attempted to do was to rerun the derivation of the quadratic formula, but in the context of a quadratic congruence, where you're looking for solutions to this quadratic polynomial congruent to 0 modulo p. So we're attempting to play the same game with the quadratic equations. And we found the argument went through fair enough. But at one point we were tempted to say, well, you see, halfway through the argument you have the square of 2ax plus b equals b squared minus 4ac. And at that point you're tempted to take the square root of both sides. So you're tempted to call upon the square root of b squared minus 4ac. Except we now have to think that this is in the context of arithmetic modulo p. And up to now, we haven't discussed the notion, the idea of a square root modulo p. We understand the existence of square roots for regular multiplication, regular arithmetic. A number, within the universe of the real numbers anyway, a real number has a square root if it's positive, 0, it's non-negative. But if it's negative, it doesn't have a real square root. You have to abstract more out to complex numbers or something else if you do want to talk about the square roots of negative numbers. But within, say, the universe of the real numbers, there are no square roots for negative numbers. So we have to gain that same understanding in the context of modular arithmetic. And since they're the building blocks of all numbers, we focus on the case of arithmetic modulo prime. Okay? So what we continued to do then, yesterday, so just the very briefest of revisions, is we recall the definition of a quadratic residue. Okay, we don't actually use the terminology square roots in the context of modular arithmetic. We use the terminology quadratic residue. Okay, so so this is definition 8.1, except I'll divide it slightly differently here. So we can say W is a quadratic residue modulo P. What that means is, what the sequence of words mean, is that there exists some u such that u squared is congruent to W mod P. So if W has, in effect, a square root with respect to multiplication modulo P, and a quadratic non-residue, if there is no such u. Okay, we looked at a number of examples. Don't take this down, but these are just from my notes. Here, just to remind you, say we looked at a number of smallish primes. We just squared everything in sight in order to encounter what the quadratic residues are and what the non-residues are. For instance, when we looked at modulo 17, we found we had, so there are modulo 17, there's 16 non-zero things, so 16 congruence classes to think about. under multiplication modulo 17, we found 8 of them were residues and 8 of them were non-residues. We just discovered that just by taking all 16 of the numbers between 1 and 16 and squaring it and see what was generated. Which numbers were squares and which numbers weren't. Of course, it's obvious that 1, 4, 9, and 16 are quadratic residues. 1, 4, 9, and 16 are already obviously squares because they are square integers in the usual sense. What's less obvious, what was there to discover, was the fact that 2, 8, 13, and 15 were quadratic residues. They are the square of something under multiplication modulo 17. And the fact that all these other numbers, 3, 5, 6, 7, 10, 11, 12, 14, the fact that they aren't, that was there to discover as well. Okay. And from looking at, okay, so I'm not going to relive the whole lecture, but from the other examples we looked at, we observed some things. We always found this equal splitting. Half of the things were residues, half of them weren't. So that's something we saw in each of the examples. So that's like a conjecture for us now. Perhaps when you look at any prime, we will always find that half of the things are residues, half of them aren't. That's up for debate. That's up for, we can try and prove that. We also spotted, since we motivated all this discussion by talking about regular square roots, so positive numbers have square roots, negative numbers don't, and there is this structural pattern you see when you're multiplying positive and negative numbers, that positive times positive is positive, negative times negative is positive, and if you do one of each, positive times a negative, you again get a negative. There's that structural pattern in multiplication of positive and negative numbers. We also floated the idea that maybe there was that similar structural pattern in the multiplication of quadratic residues and non-residues. And we found, by testing out a few examples, we always encountered this pattern, that residue times a residue is a residue. A non-residue times a non-residue is always a residue. And if you do one of each, a residue times a non-residue, you get a non-residue. So there, at least in the examples we looked at, we encountered the same structural pattern where residue was taking the place of positive. And that makes sense because both of them mean it has a square root. And non-residue played the role of negative. So those things are the things we would like, so I look at my notes. Yeah, those are the things we'd like to investigate now today. Okay. But any questions just off the definition or anything about the definition you'd like me to clarify? So that's the main idea. W is a quadratic residue if it has a square root. Although I'd like to train myself to stop saying square root. But there's not wrong. But just when you see it in print, it's always, they talk about quadratic residues and quadratic non-residues. So quadratic residue is something that's left behind after you square something. Left behind meaning it's a remainder under division. Division by P, remainder, or it's congruent to W. So we now encounter theorem 8.1. It's proved out there in the notes, so I'll replay the argument here in the visualizer just so we can discuss it bit by bit as we go. And so let P be an odd prime. That's it. This expression you see many, many times when you're reading number theory in maths books. It just means, what it means is you're talking about a prime number except 2, not 2. Okay, but people seem to like that phrase, let P be an odd prime, and it seems a bit more mysterious than it is. It just means some prime number apart from 2. There's not that much going on modulo 2. There's not that much to discover, really, modulo 2. 1 is a quadratic residue. There you go, that's the end of the story. Modulo 2, so it's not that interesting. Really, we're interested in what goes on typically for prime numbers. So this theorem is going to say of the p minus 1 non-zero congruence classes, these are the things that we investigate under multiplication modulo p. 0 isn't that interesting to investigate, so it just kills everything under multiplication. But of the p minus 1 non-zero congruence classes, p minus 1 over 2 are quadratic residues. And so the other ones have to be non-residues, because a non-residue is something that isn't a residue. So half of them are quadratic residues, and the other half are non-residues. Of course, if p is an odd prime number, then p minus 1 is even, so p minus 1 over 2 is an integer. But you can split the non-zero congruence classes into two halves. I haven't said it there. Congruence classes are quadratic residues, of course, modulo p. And this proof basically just generalizes the technique we were using when we were investigating the examples. We looked at the few early primes, 17 or whatever. What we did there was we just squared everything. When you square everything, you encounter what the squares are, and observe their values. And the ones that you don't see coming up as values of squares, they're the non-residues. So we just replay that argument, basically. So first of all, we claim the list. So we're going to square 1, we're going to square 2, we're going to square 3, etc., all the way up as far as p minus 1 over 2. We claim that this list contains all the quadratic residues. Okay, this is clearly a list of quadratic residues, because they're all obviously squares. They just are. They're all the square of something. But you see, I've stopped at the halfway point. This is the question I posed to you yesterday. Somebody spotted it, that I don't have to go ahead and square the second half of numbers, right? Because the second half of the list are just the negatives of these ones. So when I square them, I get the same values that I've already listed. So this contains all the quadratic residues, since squaring any other congruence class, so this is going to be a y which is strictly greater than p minus 1 over 2, but less than or equal to p minus 1. Just amounts to the same value modulo p as squaring minus y, which is already on the list, because if y is in the second half of elements, somewhere between p minus 1 over 2 and p minus 1, it's negative minus y is somewhere in that list that I've written down. As minus y will be somewhere between 1 and p minus 1 over 2. Does that make sense? Is that okay? Is that clear? So if you're looking for quadratic residues, you will find them in that list. 1 squared, 2 squared, 3 squared, all the way across up as far as p minus 1 over 2 squared. Now, what I haven't said yet, what we don't fully know yet is, okay, so you could say, okay, that's the end of the proof. There's p minus 1 over 2 things on that list. Just count them, 1, 2, 3, 4, as far as p minus 1 over 2. Well, there's certainly p minus 1 over 2 objects listed down there, but we have to worry about, are they all distinct? Maybe there's some repetitions on this list. Maybe when you square things, it's not a one-to-one operation like that. So we know squaring in general isn't one-to-one because when you square x and minus x, you get the same value. But maybe something else funny can go on. And moreover, by these I mean this list up here, these are all distinct. Okay, that's a little claim that we should prove, just to get it out of the way. So assume on the contrary, so we're going to do a little proof by contradiction. Assume on the contrary that a squared is congruent to b squared modulo p. A and B are two things from this list. So A and B are both bigger than or equal to 1 and less than or equal to p minus 1 over 2. And that they're different. So I'm not just taking 3 and 3, 5 and 5. I'm actually taking two different things, two different elements from this list. I'm squaring them. But I'm supposing that they're the same value after you square them. Okay, it can't be, so we're going to do a proof by contradiction. We're going to prove that a contradiction flows from them. Well, what's the definition of congruence? Two things are congruent modulo p means p divides their difference. Okay, that's just the definition of congruence mod p. And that implies that, you see, a squared minus b squared has a nice factorization, a minus b times a plus b. P isn't any old number, P is a prime number. And what's the conclusion when you have P dividing a product? It's almost an alternative definition of a prime number. P divides a product, then must divide one of the factors. The way it divides the product, it can't be because a bit of P is in the first thing and another bit of P is in the second thing, so it's a prime number, it can't be split up. So if it's dividing the product, that's good. It must divide the difference, or it must divide the sum. It can divide them both for sure. Then in fact, you'd actually have P squared dividing it at least. But it must be true that it divides one or the other. So we're just going to investigate both of those cases and just show that both of them are contradictory. Neither of them can actually happen. If you think about a plus b, so think about a plus b, for instance. Now a plus b are both bigger than 1. So a plus b, whatever it is certainly bigger than or equal to 2. Just the integer a plus b is bigger than or equal to 2. But a plus b are both less than or equal to p minus 1 over 2. So the absolute largest that a plus b could be would be p minus 1. Are there any multiples of p between 2 and p minus 1? For example, if p were 17, I'm saying, are there any multiples of 17 between 2 and 60? No, it's just not. The closest multiples of p to that interval are 0 and p itself, but both of them are excluded from that. So there's no multiple of p in this interval. So that implies p does not divide a plus b. So it can't be that p divides a plus b, On the other hand, if you think about A minus B, think about the smallest and largest that A minus B can be. So basically, you're looking at two numbers here in this interval between 1 and p minus 1 over 2, and you're wondering how far apart could they be? Well, the furthest apart they could be, they certainly can't, the distance between them has to be strictly less than p minus 1 over 2. Okay? Because these are two numbers between 1 and p minus 1 over 2. Now, I don't know which of A and B is actually the bigger, so this is either going to be minus p minus 1 over 2 is less than this, or less than p minus 1 over 2. Yeah, that's clear? A and B started off between 1 and p minus 1 over 2, so the furthest apart they can be, you move them right to the edge, A at one end and B at the other end. Whatever that distance is, it's certainly strictly between these two. And how many, are there any multiples of P in this interval? Basically minus a half of P all the way up to plus a half of P. Well, there is one multiple, namely 0. 0 is a multiple of P. But also, A minus B is not equal to 0 since we assumed up above that A was not equal to B. So there's actually no multiples of P there either. So P does not divide A minus B. It's just where A and B have come from. You can't have the difference being divisible by P when A and B are different. So but we said up here that P must divide A minus B or A plus B. But here we're now saying that it can't divide either. So this is a contradiction. This is a contradiction with this statement here, star star in the box. So that's a problem. So what led to the contradiction? What led to the contradiction was this assumption up here, where we assumed that two of these numbers in my original list were actually the same congruence class modulo P. So that's not true. So that assumption is wrong. So all the P minus 1 over 2 elements in the list star are distinct. So that proves the theorem. This list has P minus 1 over 2 things in it. They are all quadratic residues, and there's no other quadratic residues to be found. Is that okay? Any questions about that, or things you'd like to ask about that? Okay, so that's good progress. From our look at the examples, we formed that conjecture. Half of the things were residues, half of them weren't. We've now proved it. When we're talking about congruence classes modulo P. The next thing we'd like to tackle is this structural pattern of how they multiply. So the other pattern we observed in our examples was residue times residue was another residue, non-residue times non-residue was a residue. And when you do one of both, residue times non-residue, that was a non-residue. So this is the pattern that's mimicking what happens when you multiply positive and negative numbers. Okay, did I write them all down right? Yeah. So we'd like to prove that this is those things. We can look at any number of examples we want to. We can continually observe this. You might get more and more confident in it, but you can never claim to have fully proved it just by looking at a lot of examples. We got to come up with a general argument that proves it. But we've got quite a lot of ammunition already. We've got a good understanding of basic facts of multiplication modulo p. We know how to do that. We know basic facts about it. We also have the theorem we just proved, which is a counting argument. We know that modulo p, we know exactly how many elements are residues, how many are non-residues. So those two ideas, it turns out, are enough to prove these properties. So there's three cases to three types of things to prove. So firstly, we'll let u and v be residues modulo p. So p is an odd prime, p strictly greater than 2. Now what does being a residue mean? Being a residue means that there exists two other things such that u is the square of alpha and v is the square of beta. That's what it means to be a residue. Now here we're dealing with two residues. We're going to multiply them together and look at the product u times v. V, a residue. Is u times v a residue? If you claim it's a residue, you're tempted to answer yes. You have to tell me what goes in, what fills in the blank, what goes in the bracket. It's very much a case of saying what you see. Say what you see. Alpha, beta, yeah. What are we using there? We're just using basic properties of multiplication modulo p. If alpha squared is u, beta squared is v. Alpha squared times beta squared, well, that squaring operation, you can take outside and apply it to the product alpha b. Okay. This multiplication is commutative here. So this alpha beta, you can organize that as alpha squared, beta squared. So it's all the same. So yeah, u times v is a residue because it's the square of that thing there. So that proves this first pattern. Residue times residue is a residue. Yeah, everybody happy with that? Seems quite clear. That's the easiest one. The other two are maybe a little harder. Let's go for this one now. Let u be a residue and v a non-residue. Modulo p. Now what does this mean? This means that there exists an alpha such that u is the square of alpha mod p. And b is a non-residue, so b is not congruent to the square of beta mod P for any beta. You can never write V as the square of it, because it's not a residue. It doesn't have a square root. Just because I said it. V is a non-residue. Okay? We're dealing with this case, we're dealing with this case here, residue times non-residue. So you use a residue, V is a non-residue. What are we trying to prove? We're trying to prove the product, what we observed in the examples, the product should be a non-residue. Just like positive times negative is negative. So we want to show that the product of U times V is also a non-residue. I should be saying quadratic non-residue all the time, but that's understood. Could talk cubic residues, quartic residues, quintic residues. Just focus on quadratic residues. Okay, how are we going to prove that U times V is a non-residue? It's a little bit tricky to prove that directly because it's a non-residue if there's the non-existence of a square root. It's a bit hard to prove the non-existence of something directly. You prove the existence of something directly by offering it up and exhibiting it. To show that something does not exist, you have to come at it from the back, so to speak. So we have to do a little proof by contradiction. Suppose it were. Suppose U times V was a residue. Okay, it's not going to be. We're going to prove it can't be. But we suppose, for the purposes of proof by contradiction, suppose it was a residue. I.e., suppose there exists I've used alpha and beta, so there exists a gamma such that U times V is congruent to gamma squared modulo P. Okay, supposedly that can't happen, but we're temporarily pretending it can. How can I get a contradiction out of this? Well, I got to use any assumptions I've made. I've assumed that U is the square of alpha. So this means alpha squared times V is congruent to gamma squared mod P. What might we conclude from that? Tempted to do. See, I've used that assumption that U is the square of alpha. The only other thing I have to make use of is that V is not the square of anything, because V is a non-residue. But down here, V is in the company of a lot of squares. Tempted to isolate V. And what do I say in this context? I don't divide both sides by alpha. I multiply by the multiplicative inverse. Yeah. So I'm going to multiply by alpha to the -2. And of course that reorganizes to the square of alpha inverse times gamma. Where by alpha inverse I mean the multiplicative inverse of alpha modulo P. That's clear from context. That's how negative indices work. How multiplication works. So, but that's strange. That proves that V is a quadratic residue. Okay? Because look, it's the square of something. There's something in the brackets there. Alpha inverse times gamma is a perfectly good congruence class, modulo P. Certainly, remember there was this issue, not everything has a multiplicative inverse modulo n. But if these are non-zero congruence classes modulo P, all the inverses exist. So there are inverses for everything. So this looks wrong because it contradicts this fact that I said up here that V was a non-residue. So something has gone strange. I can't have both of these things being true. white is black, up is down. You just can't have that. So what's gone wrong? What's gone wrong was this supposition here. This thing here is, you cannot, after you assume that V is a non-residue and U is a residue, you can't go and then pretend that U times V is a residue, because it leads to a contradiction. Okay? So this clearly contradicts here, star, up here. I'm in another argument now, so I'll start to reuse these asterisk labels. So this clearly contradicts star, because V is supposed to be a non-residue. So the assumption at star, this one here, supposing UV was a residue, is wrong. That assumption is wrong, so it leads to contradiction. So the conclusion then is U times V is a, well, if it can't be a residue, it has to be a non-residue. Yeah. Non-residue. So that's the second of those patterns. Residue times non-residue is non-residue. So residue times non-residue is a non-residue. Prove that. So there's one more. Non-residue times non-residue is residue. So we proved the first one directly using the two square roots. We proved the second one with a little proof by contradiction. And for the last one, we need something a little bit of a stronger argument, a little bit of a more complicated argument. So now let U and V both be non-residues. Let U and V both be non-residues. We want to prove, what we want to prove is that UV is a residue. We want to prove that U times V is the square of something. Now this is harder to approach directly because the assumptions we have, U and V both being non-residues, those assumptions are kind of weakish in a way because they mean the non-existence of square roots for these two numbers, for these two congruence classes U and V modulo P. So we need something a little bit more. So we'll need to use a counting argument. What's a counting argument? Counting argument is when you count some stuff and divide people up to hard to see what it is. So we'll use a counting argument based on the theorem we just proved earlier today. Theorem 8.1. That there's exactly half of the congruence classes are residues, half of them are non-residues. And together with the results we've just proved, that residue times residue is residue, and residue times non-residue is non-residue. So let Z1 up as far as ZP minus 1 over 2, let these things be the residues. Okay. Note, U and V are not on this list. U and V are not on that list because U and V are non-residues. Z's are all the residues. we've seen that each product U times one of the Z's, that's a non-residue times a residue. We've already seen that each of these is a non-residue. Okay, we'll prove that. There are clearly p minus 1 over 2 such products, because there's p minus 1 over 2 possibilities for Zi, Z1 to Z p minus 1 over 2. And each congruence class UZI is distinct from all the other ones. Because if you did have UZI congruent to UZJ, we just cancel the U's. Zi congruent to Zj. So if you take different Z's, multiply them by U, you get different products, different congruence classes. So the U times Zi, where I goes from 1 to p minus 1 over 2, these are all the non-residues. And that makes use of the theorem as well. The theorem tells us there are p minus 1 over 2 non-residues. Here's a list, U times Zi for each I. There's a list of non-residues, and they're all distinct. So it must exhaust all of the non-residues. That must be all the non-residues. UZ1, UZ2, UZ3, etc. up as far as UZ p minus 1 over 2. This is what we mean by a counting argument. Counting up the possibilities and drawing our conclusions from that. So the product U times V must be another kind of thing entirely. Okay? It can't be congruent to any of the UZIs, because then the Zi will be congruent to one of the V's, but we've already said V is not on that list. So the product UV must be a different congruence class to all the UZIs. Okay? And the UZIs completely use up all the non-residues, so the only possibility left is that UV is a residue. That's what we mean by a counting argument. UZI uses up, it exhausts all the non-residues by things we've already proved. So U times V must be a residue. Quadratic residue. Must be something else. It can't be any of the UZIs. The UZIs exhaust all the non-residues, so U times V must be a quadratic residue. So that's good. That completes. That means I can stick a tick on that one. So that's good. That's more progress. Another feature that we observed from our examples, we've been able to prove. Any questions or queries about any of those? Yeah, go on. Okay, so this last thing I'm trying to prove, I take two non-residues. I'm trying to prove their product is a residue. Think of negative times negative as positive. That's what we're trying to do. So the way I do it is, well, if I want to prove that U times V is a residue, I have to come about it in a roundabout way. So the way I do it is I say, well, by the theorem, I can write down this list of all the residues. And I know there's p minus 1 over 2. That's why they go Z1 all the way up as far as Z minus 1 over 2. We've already proved that non-residue times residue is non-residue. That was the second pattern we proved. So I know that U times Zi is always a non-residue. How many non-residues are there in total from the theorem? P minus 1 over 2. How many of these products UZI are there? P minus 1 over 2. So P minus 1 over 2 choices for Zi. They're all non-residues. They're all distinct. Because if you had UZI equals UZJ, just cancel the U's. Zi is the same as Zj. So these are all distinct congruence classes. There's P minus 1 over 2 of them. They're all non-residues. So they exhaust all the non-residues. So when you go and take another element, namely this V is not any of the Z's, because V is a non-residue. So when you look at the product U times V, again, that can't be equal to U times Z for any of the Z's, because you could just cancel the U's and V would be equal to one of the Z's, which is. So this U times V must be something else entirely, not a non-residue. So there's only one other kind of thing, a residue. Does that help? Yeah? So it's a much, the first property was bang, 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 proof directly. Alpha exists, beta exists, square the product, that's UV. That was very direct. Second one, a little bit more weaker, or more roundabout way, proof by contradiction. And the third one, a little bit more scenic again, based on accounting. Okay, that's good. We've already made good progress. We've formed 2 conjectures from our samples, and we've managed to do them in general. We'll continue with this next week.